microphone. Yeah. The next speaker is Sheffet, and he will tell us about all techniques for observing differential privacy.
Yeah, I guess it's like Anchor. I also changed the title of the talk. Everyone talks about new stuff. I want to talk about old stuff. Okay.
Classic stuff.
Okay. Okay, so whenever, this talk is about differential privacy, and whenever I talk to non-experts about differential privacy, I give them I start with the spiel that it is the notion that into my analysis I'm going to introduce, is it too loud? Is it just me? Okay, into my analysis I'm going to introduce cleverly designed and carefully calibrated based on your data and your analysis, random noise into your analysis that will mask out the effect of any single person. I am fully aware that when they see this, I even tell them, they should be infuriated. They should see it and say, you want to take my data and you tarnish it with random noise, and that's inconceivable. How can you do that? And I tell them, take that infuriation and table it. That's not what I'm going to tell you. What I'm going to tell you is that, in fact, there are many analyses out there that are using randomness as is. And as it turns out from this talk, these analyses, when they're calibrated correctly, also preserve differential privacy. And it's a non-worst case, so when the inputs are nice, you can literally take them and run them as is. Okay, so now that I've given you the natural version of the talk, the longer version of the talk will be like this. But yeah, I will start with a spiel on differential privacy because I know that not everyone here, I'm pretty sure that everyone have heard of differential privacy, but I'm not sure that everyone really get the idea. I'm not sure that I would help. Maybe I'll confuse more, but I'll try. I'll talk a little bit about private linear regression, then I talk about more linear regression related and lovely distributions that are connected to Gaussians, and finally conclude with the privacy theorems. Okay, so what is differential privacy? To give the definition of differential privacy, you first complicate life and give another definition. Neighboring data sets are data sets that differ just in a single person. All other n-1 people are the same. Someone opts in, opts out, or changes into whatever outwardly creature. And then an algorithm, a randomized algorithm, is said to be differentially private if the following game happens. You choose any neighboring data sets, differ just on one person, and you know the data sets and you know the person they differ on. I'll pick one of them, I'll run my computation over one of them in secret and show you the output. And even though you know that it was one of these two data sets and you know the result of my output, you still are not really able to figure out whether I used the one or the other. And to actually formalize it, we use a quantification. We say that the algorithm is epsilon delta differentially private, where epsilon controls the multiplicative version of how much the outcome is more likely to appear or not, and delta controls the additive version, the additive term of the change into the probability. And the classic algorithm that preserves differential privacy is the additive random noise mechanism that basically says, well, if I have a query and you extend the query on data sets and how many people satisfy so-and-so property, this query exhibits low sensitivity. When I change only one person, only the value of the query changes by no more than one. So what I'll do is I'll actually take the value of the query and add to it some random noise, hence the name additive random noise. And you can see for yourself, right? If the value of the query is 17 on one data set and 18 on another data set, and I picked one of them and I sampled 20.03, you look at the result of my computation and say which one is more likely to come from, the blue distribution or the red distribution. Yes, the red distribution, but not by a lot. That's why I'm preserving privacy with this additive random noise approach. Now, as I said, I am going to tarnish the computation. I'm introducing error into computation. That error, of course, is independent of n. So the classical approach, the classical triangle that we have in differential privacy analysis is privacy versus accuracy versus the size of the data. If I want a good guarantee of privacy, not too much privacy loss, and if I want a good guarantee of accuracy, being fairly close to the true answer, the size of the data has to be large. And differential private analysis about the trade-off between these three quantifiers. Okay, linear regression, we all know and love linear regression. It's one of the things that people do on many data sets. You know, someone comes and asks me, oh, predict this particular y as a linear function of all the other x's. And I open my undergrad notes and I run the linear regression computation, and I find the linear regressor. And since it's one of the most basic things that people want to do on data sets, the question is, can we do it with differential privacy? And the answer is yes. I mean, Kamalika is not here. She was here yesterday, but it's her work that started it. And in fact, there are multiple techniques to doing private linear regression that use the additive random noise, either on the output or in your objective function, but it's the additive random noise. Just as a comment, both of these techniques require that my loss function is regularized because I need to control the sensitivity of this linear regression query. Okay? Now comes the fact that on a data set that has many attributes, people will want to run many regressions. You would want, you know, this maybe y in this particular x, or this particular x, or a different choice of y and a different choice altogether of x. A data set with the dimensions can yield exponentially many regressions, indeed. So we can solve all of them if I just publish the second moment matrix of the data. Because if this is the one quantity, all the variances and covariances between the different features, that will allow you to run any regression you want on any number of variables. And because it's such a common thing to do, there are also known algorithms to how to release the second moment matrix. One of them of Dworkin, like every other paper in the differential privacy Dworkin, just uses the additive Gaussian noise on the matrix itself, on the second moment matrix itself, and releases it. And they analyzed it for the terms of PCA. Okay, so this concludes the overview. Hopefully, now I'll start to talk about things that were new to me, at least, because I'm not a statistician.
Somehow the definition that you presented for differential privacy seems suited for discrete valued things, but here you're going to output parameters which are real numbers. So is this the same definition?
It's the same definition. It's well, when I release the output of my mechanism, right, with the additive random noise, it's a real number. Right? And it's the definition. I glossed over it, but
satisfying the definition, that is.
Yeah, but it would.
Okay.
It would be the same definition. It's for any subset of the reals. Okay. Okay. Linear regression, as everyone knows, has been extensively studied from the days of Gauss, and you know there are, I think, 500 books about it in the University of Alberta alone, and I'm sure here in Berkeley there are many more. I, of course, have not read them, but in all the literature about linear regression, none of the existing techniques of linear regression uses this additive Gaussian noise mechanism. None of them take the second moment matrix of the data and add to it random Gaussian matrix. They do a variety of other things. They do a variety of regularization. You know, people talk a lot about the Lasso regularization that helps people find sparsity. But in this talk, I actually want to talk about the Ridge-Regression, or L2 regularization, where to the classic problem of linear regression, I'm adding this L2 penalty term. And you know, the standard approach of what should be the penalty term, how do I find the actual coefficient here? Try all 32 flavors. You know, try them, run your regression in multiple variation, in multiple values of this lambda, take the one that minimizes the risk. It depends on the data. And the approach I'm going to talk about here is, you know, completely data independent. It's going to set this lambda to preserve privacy. This Ridge-Regression comes with numerous justifications in literature, or different ways to look at it. First of all, you can see it as the Laplacian of solving the regression with a bounded L2 norm. Lagrangian, sorry. The Lagrangian. Yeah, sorry. That's the problem with speaking. You lose IQ points when you're talking in front of audience. Anyway, the Lagrangian of a bounded L2 problem. A different way to see it is that I take my original data that had n observations, and I paired it with particular d-1 or d points that are, the identity over each feature and 0 over this y. Or I can even do it completely with the identity over the O feature, lambda times the identity on all those features, because the last one will be all zeros on x, so it won't change the value of the optimization, or it won't give me a different minimizer. And a different way to see it is to say that this is a Bayesian version of the linear regression. I start with a prior on the betas, sampled from a spherical Gaussian. And I know how this spherical Gaussian relates to the standard error in each observation. And based on that, I'm updating to the posterior distribution. And this beta R, the one that solves the Ridge-Regression, is the maximum a posteriori of the problem. Based on that, you can start thinking onwards and say, what else can we do with linear regression and these types of penalty terms? There are two other options that I've considered. One is using a random regularization. Rather than adding this particular term to my objective, let's use a random term, right? Random features, random labels. Let's use that. Let's pad my data with that. Or let's pad my problem with this particular random set of examples. A different version is, maybe instead of doing the maximum posteriori of the Bayesian posterior, I'll sample from the posterior distribution. Now, I can do it for the beta itself, but it requires me to know the variance of each observation, which can be computed, but I'm not going to talk about it here. Here's an alternative approach to this Bayesian sampling. Don't sample the beta, sample the variance covariance matrix from the posterior distribution. So have a prior on the variance covariance, update that prior based on each observation that you see. You get a new posterior distribution, sample from it. Okay? And then inverse Wishart, it's the simplest, I don't know if it's the simplest, but it's a rather simple conjugate prior that people use for this posterior sampling, or the posterior distribution. Okay, so now that I've introduced this inverse Wishart, let me say what are those Wishart and everything. What are all these distributions? Gaussians are great, right? We all love Gaussians. And we love them so much that, what's better than a Gaussian? Two Gaussians or multiple Gaussians, right? Sample many IID Gaussians. And now that I have multiple IID Gaussians, I can look at the norm of what I get. Right? If this is the vector observation, I can look at the norm of this vector. And it turns out that it's tightly concentrated around k. This is the chi-square distribution. Because everyone loves Gaussian, so we came up with new distributions. The chi-square distribution is the distribution on the square norm of this vector. And I can also manipulate those manipulate linearly the Gaussians to get a multivariate Gaussian. And that's a definition, basically, of a multivariate Gaussian. And then, now that I have access to a multivariate Gaussian, like Ankur, and instead of just using one dimension, let's use multiple dimensions. I'll sample many examples from this high-dimensional Gaussian. And then I'll look at the second moment matrix of my samples. And that's called the Wishart distribution. And it has a closed form for its PDF. In fact, people like the Wishart distribution so much that they invented the inverse Wishart distribution, which basically says my matrix comes from the inverse Wishart distribution if its inverse comes from the Wishart distribution of the inverse scale matrix. Okay, now armed with all of these definitions, I can basically give you can give you the theorems, the privacy theorems, that using additive Wishart noise or sampling from the Wishart distribution or from the inverse Wishart distribution, all of those preserve epsilon delta differential privacy. Given that the matrix that I'm using has large enough scale. So what I'm talking about basically is more about the sampling. I need the sampling from the Wishart distribution that my scale matrix is well spread, has large eigenvalues. But basically what we started with, this triangle of privacy versus accuracy versus the size of the data, now becomes a niceness property. If I want low privacy loss and good accuracy, I better use the sampling on really nice matrices that are very, very well spread. And the trade-off now goes between these three parameters. Questions? Or okay. Feel free, by the way, to ask questions. Here is the Cliff Note version of the theorem, the privacy theorems. Basically, if I have a matrix and observation, each one of them has a bounded L2 norm, then each of the following algorithms is privacy preserving. Take the second moment and use additive random noise from the Wishart distribution. Parameters has to be set. Or if the data is nice, all the singular values are greater than a particular W, and this is the format for W, then I can sample from the Wishart distribution or the inverse Wishart distribution. So this always works, and this only works if the input is nice.
What's the difference in one is
you take the actual the vis-a-vis, and you add to it random noise, a sample from this distribution. This is the additive random noise, right? Take the output of your query and add to it random noise. You seem confused. So what? Two is say, here is a certain particular threshold that I need. All the parameters are mixed together into this threshold. If my data is nice, if it is well spread, then I can sample from the Wishart distribution centered around the VCV or from the inverse Wishart distribution centered around the VCV, and it will preserve privacy just outputting that sample.
Whereas in one, you're taking a sample from essentially the identity matrix around the identity matrix.
Yes.
Whereas the other one, you're sampling around the covariance matrix.
Exactly. And because this definition of niceness is so simple, then when the data is nice, I can actually use it as is. When it's not nice, I can make it nice. And this making it nice, padding it into making it with large enough singular values can be done in a way that really correspond to these analyses. For the first one, it's like it will correspond to the Ridge-Regularization. And the second one, it will correspond to a well-spread prior. I'm assuming a well-spread prior. I update it. The posterior will also be well-spread. So I'm sampling from it. And it will be nice. So just to recap this analogous thing, the additive random noise, the Dworkin et al. Paper, I don't think there is an analogous existing technique that corresponds to it nicely. The sampling from a Wishart distribution is like you projecting the data with a Johnson-Lindenstrass transform, and it will correspond to the Ridge-Regression. Sampling from the inverse Wishart distribution will correspond to sampling from a posterior distribution, according to Bayesian analysis. And the additive Wishart will correspond to either using random regularization or padding my data with random set of points. But the beauty is that all of this have been studied before. Like, this is a really tight, really small list of CS papers that talk about linear regression that have been extensively studied in statistics. So Ridge regression, Bayesian, the use of random regularizations have all been studied before. So we can literally take those techniques and use them as is, or use their utility analysis as is. The thing that needed proof is that why is that actually preserving privacy? Okay, so I gave you the privacy theorems. Yeah, I have enough time, so I think what I want to do is actually give you the proof overview for a very simple one-dimensional case for at least the additive version. If there are any other questions. But at least on the one dimension, let's consider the case where a very simple input, my data is a vector of zeros and ones. So d transpose d is just summing up those di squared, which will just summing up the di, because they're 0 and 1s. So a d prime differs on one entry.
I'm confused. D was the code. What matrix? It was a matrix to begin with.
Yeah, it was a matrix. Now I'm saying let's take a matrix of one dimension, the simplest thing, right? And even discrete input to make it even simpler. And then d prime transpose d prime is basically d transpose d plus 1. Just the number of ones.
Plus or minus.
Plus or minus, but plus. I chose plus. Okay. So basically, can I erase the directions? Sorry, Avram. So basically, I'm sampling from I'm padding, what I will do, this additive Wishart will be sample sample from a chi-square distribution of k's degrees of freedom, and then just publish. I either publish.
What is K here?
It's a number degrees of freedom, and that's the number of examples. This is the particular form of K, which happens to be dependent on d plus something dependent on 1 over epsilon rather than times. That was quite surprising and took a little bit of effort, but in our case, d is 1, so it's basically 1 over epsilon squared. So I'm either releasing this d transpose d plus the sample, or I'm releasing this d transpose d plus 1 plus my sample. So I'm comparing the PDFs of the two distributions. It's basically getting A from this chi-squared, getting A versus getting A minus 1. Right? Because if the value I got was A, it was some sort of x, then I got this x minus this d transpose d in here, and x minus 1 here. Okay, chi-square distribution is proportional to, sorry, it's PDF. It's proportional to x to the k over 2 minus 1 times e to the minus x. So what I will get here is just a to the k over 2 minus 1, a minus 1, k over 2 minus 1, e. Oh, so, there's a half here. Yeah, sorry, it's x minus over 2. And e to the half. And just a little bit of arithmetic manipulation, this would be 1 minus times e to the half And this is at most e to the k minus 2 over a minus 1 half plus half. Hope this is not too low for you guys to see. So remember, a is what I sampled from the k-squared, from the chi-square distribution. And it is known that because Gaussians are tightly concentrated around the mean, then the chi-square distribution is tightly concentrated around the mean. So it is known that with probability greater or equal 1 minus delta, a is in the range of square root of k plus minus, I'm pretty sure that this is the full version. So it'll be roughly k plus O of square root of k. Which means there's some minus here that I forgot. That should be e to the minus half. So what I end up getting from there, the exponent of this minus half plus half of k minus 2, k minus, I don't know, 8 square root of k ln 1 over delta. I'm glossing over constants. And this term is very close to 1. And because of these are in opposite signs, this half minus half plus half of 1, and then this is roughly like plus 8 square root of k over k. So everything here is upper bounded by e to the minus 1 over square root of k, and I'm neglecting constant factors. I'm not sure that you've been able to follow, but what's really going on here is something that is in common to all of these proofs about Wishart. In the standard case, our ratio of PDFs has these two terms. One comes from the determinant, which was its one-dimensional equivalent was this, the polynomial term. One comes from the exponent. Some linear manipulation carries this to the exponent. And then in my exponent, I get a sample from a chi-square distribution minus its mean. So the proof of privacy actually goes through the chi-squared concentration distribution, or the Johnson-Lindenstrass, saying that this is not far off from what it's expected to be. And for those of you who do know something about differential privacy, this is how you bypass the off-the-shelf composition that will require some log factors. This omits the log factors by looking at the exact distribution. So basically some quantity x and some sample from a chi-square distribution centered around the same thing, and I get a difference which is about square root of this value. Okay, if you were able to follow, great. If not, that's also fine. That's basically what I wanted to tell, and I'm done.
Is it sort of natural to think of this as sort of saying, in regularization, if you're wanting to generalize, you probably don't want to let any single data point throw your regression off. Mm-hmm. And so regularization tries to avoid that. And that's almost exactly the same sort of thing that you want from privacy, which is you don't want any single data point to be revealed in the result.
Exactly.
So does that analog really motivate a lot of this?
There's a notion of stability that captures both of them precisely. That stability implies generalization, and stability, in some sense, is equivalent to privacy.
Yeah. And it's precisely that. And as much as I would love to take credit for it, as I said, Kamalika and Claire and Anand, they started with the regularization. Like, you need this regularization. What sort of is my contribution is the fact that you really need nice instance to do the sampling. Like, you can't have them really tightly concentrated, and that's sort of like the regularization.
So like typically if you use like stochastic descent to solve these things, wouldn't that also in fact give you stronger guarantees because you're every time you're sort of taking a random sample descent step?
There are ways to solve it for stochastic, using stochastic gradient descent to preserve privacy. That's completely true. The only thing is that that will be for a particular regression problem. That's not for the releasing the VCV matrix. I do not know how to do gradient descent with releasing the VCV matrix.
Any more questions? Okay, so if no more questions, then let's thank Or again.